How's it going, guys? Today in this video, we're going to be going over module 13.4. It's the only day of this module. But in your notes, we do start out with a warm-up. So if you haven't done it, pause the video, give it a try. But I'm going to go ahead and just get started with it. With number one, our A value is negative, and our K is -9. And we're asked to find the range of the function. So to find the range of the function, that's going to depend on your A and your K. If your A is negative, that means you're reflected over the x-axis. That means your function of y is less than the asymptote. That's at -9. So your A is negative, it's going to be y is less than your asymptote of -9, or y is less than k. Number two, given f of x equals a times b to the x, f of x is an exponential growth function if b is greater than 1. An exponential growth function, your b has to be greater than 1. A's don't do anything to determine if it's a growth or a decay function. Number three, given g of x equals 7 times 5 times x plus 4, all plus 9, we need to figure out what the range of the function is going to be. So again, our range depends on our a and our k. So our a is positive. That means our function did not reflect over the x-axis. That means we're still above the asymptote. So our function of y is greater than our asymptote at 9. So if a is positive, it's y is greater than your asymptote or your k. And number four, given f of x equals a times b to the x, f of x is an exponential decay function if b is between 0 and 1. And again, a's don't do anything to tell you if it's a decay or a growth function, so you can cross those out right away. So let's go ahead and get started with the notes. For 13.4, we're talking about the base of e. So even though e is an irrational number, it can be used as the base of an exponential function. The number e is sometimes called the natural base of an exponential function, and I'm sure you guys have seen it in your science classes many times before. E is an important number, and what e is worth, or what it stands for, or not what it stands for, but really the value of e is that e is approximately 2.7. So e is about 2.7, or you can say about 2.72, whatever you want to say. It's about that value. And what I want you guys to do is I would actually prefer you guys to pause the video and try this problem out yourself. Since e is about 2.72, that makes this function an exponential growth function. So you're going to fill out this table, graph it, and fill out these properties very similarly to the way you would any other exponential growth function. So if you haven't already, pause the video, try it out. I'm going to go ahead and get started with it. So for number one, for the table, when x is -2, we're going to plug that in. E to the -2 is approximately 0.14. When x is -1, our e of x is 0.37. When our x is 0, e to the 0 would just be 1. Anything raised to the 0 power is always 1. When x is 1, we have e to the 1, or just the value of e, which we said is 2.72. And then when x is 2, we get e squared. So that's going to give us about 7.39. So these are our values of f of x. So we're going to go ahead and plot these points. So when x is -2, we have 0.14. Let's say just about there. When x is -1, we have 0.37, right about there. When x is 0, we have 1. When x is 1, we have 2.72, just about there. And when x is 2, we have 7.39, right around there. So our function is going to look something like that. It's an exponential growth function. And since it is an exponential growth function, that means we have an asymptote at y equals k. And since this is our parent function, our k is 0. So our asymptote is at y equals 0. We still have an asymptote because it's still an exponential function. All right. And since it is an exponential function, the domain is going to be all real numbers. Every exponential function has a domain of all real numbers. and the range is going to depend on your a and your k, just like every other exponential function. So our range, every y value such that y is greater than 0. Our a is positive and our k is 0. So y, the function y is above the asymptote of 0. So y is greater than 0. Is the function increasing or decreasing? To determine if it's increasing or decreasing, that's going to depend on your y values, or rather what's happening to your y values as x increases. So if x is increasing, we see our y values are also increasing. So that means the function is increasing. If the y values were decreasing as x increases, that'll make it a decreasing function. For number 5, the function's y-intercept. The y-intercept always happens when x is equal to 0. And when x is equal to 0, we plug that in. We get the point 0, 1. Number 6, another reference point on the graph that can be used as a reference point. So the point 0, 1, for every exponential function, we always use that as one of our reference points. So our other reference point for this function is going to be the same exact reference point we use for other growth functions, which is 1b. Remember, for exponential growth functions, we always use 0, 1 and 1b. And for the case of our basis being e, our b is always e. So anytime you have a base of e, our other reference point is always just going to be 1e, since our b is going to be equal to e for these types of problems. Next, we need to identify the end behavior. Since this is an exponential growth function, it's going to have the same end behavior as every other growth function. So as x goes to infinity, f of x is also going to infinity. You can see that on the graph. As x is increasing, y's are also increasing. So as x goes to infinity, f of x is also going to infinity. And when x goes to negative infinity, your f of x or your y's are going to 0. As your x's decrease, as you're getting smaller and smaller with the x values, your f of x gets closer and closer to 0. So it's approaching 0. So that's what we say. F of x is going to 0 as x is going to negative infinity. For number 8, there's a horizontal asymptote at y equals 0. We already talked about that. Our asymptote is always y equals k. So we have asymptote at y equals 0. So let's keep on going. Here we're talking about predicting transformations of the graph. So for the function f of x equals e to the x, they can be transformed into different exponential functions with the base e, depending on the parameters h, k, a. Just like with other exponential growth and other exponential decay functions, we do not actually affect our horizontal, we don't affect the graph horizontally. We don't have any horizontal stretches or horizontal compressions, and we don't have any horizontal reflections like reflections over the y-axis. So we can only affect it by translating it left and right, translating it up and down, and stretching it vertically or reflecting it vertically over the x-axis, just like other exponential functions. So what would change the domain? Just like with other exponential functions, nothing's going to change the domain. It's always going to be negative infinity to positive infinity. What would change the range? Reflections over the x-axis will change the range, and vertical shifts up and down will also change the range, just like with all other exponential functions. And what would change the asymptote? That would be vertical shifts. Remember, the asymptote is always y equals k. So whatever changes that k value changes the asymptote. And k changes when you shift your function up and down. Next, we're going to talk about graphing combined transformations. So our two reference points when it comes to f of x equals e to the x is the same reference points that we have for exponential growth functions. That's 0, 1 and 1b. But it just so happens that our b will always be e when your base is e. So our two reference points are 0, 1 and 1e. And your two transform reference points become h, comma, a plus k, and h plus 1, comma, ae plus k. But to be honest with you guys, I personally don't like memorizing a bunch of little formulas like the h, comma, a plus k, and h plus 1, comma, ae plus k. I don't like wasting my time with that. I prefer to just have one main formula and derive everything from that. And that's exactly what we can do with our transform reference points. Those transform reference points come from the transformation rule of x plus h in ay plus k. So anytime we plug in either of our reference points, let's say 0, 1, if you put that into our transformation rule, we'll end up getting that h comma a plus k anyway. So we have 0, 1. If you put that into our transformation rule, when x is 0, we get 0 plus h. And when when y is 1, we get a times 1 plus k. We simplify that out. We get that same h comma a plus k we had in the table. The same exact thing. And we can do the same thing with 1 comma e. We put that into our transformation rule. We get 1 plus h comma a. Our y is e in this case, so a times e plus k. So if you rewrite this, just to match our table, h plus 1 and ae plus k. And remember, this point is xy, so x is 1, y is e. So that's what we plugged it in. And this h plus 1, ae plus k is the same thing we had in the table. So we get these transform reference points from just plugging in our parent reference points into our transformation rule and seeing what we get. So you don't have to have those two memorized. It can help if you do, but if there's a lot of formulas to memorize, forget about it. Memorize the transformation rule and know how to get them by plugging in your reference points into a transformation rule. For our asymptotes, y equals 0 is the asymptote of our parent function. And just like with every other exponential function, our transformed asymptote will always be y equals k. All right, so let's go on to number 1. Here we're giving you guys a transformed exponential growth function with base e. We're going to take it. We're going to figure out its reference points, its asymptotes. It says transformations, but we really just care about the transformation rule and the domain and range, and we're going to graph it. So our a is the same thing. It's -1/2. Our b is e. Our h is 2. And our k is -1. Our transformations, if we just go through that really quickly, our a's are vertical stretches. So since our a is -1/2, we have a reflection over the x-axis and a vertical compression by 1/2. Our b is e. That doesn't transform anything. Our h is 2. So that's a vertical shift to, a horizontal shift to the right by 2. And our k is -1. And that's a vertical shift down by 1. So you should know that. You should know that. We've been going through that all year. But now let's go ahead and do our transformation rule. It's x plus h comma ay plus k. So we get x plus 2, and our a is -1/2 times our y. So -1/2 times y is a -y/2 minus 1. -1/2 times y is just -y/2. That's why I got that second part of the transformation rule. Our asymptote will be y equals k. So in this problem, y equals -1. Our first reference point, that's going to come from the parent point 0, 1. We're going to plug that into our transformation rule, and we're going to see what we get for our transform reference points. So 0, 1, you put that into your transformation rule. 0 plus 2 is 2. You plug in 1 for y, you get -1/2 minus 1, or -1.5. Our second reference point is 1 comma e. We're going to plug that into our transformation rule as well. And when we do, 1 plus 2, since our x is 1, we get 3. And since our e is our y, we get -e/2 minus 1. Our domain is an exponential function, so it's still going to be all real numbers. So from -infinity to x to +infinity. In our range, that's always going to depend on our a and our k. Our a is negative, so we're below the asymptote. So it'd be every y value such that y is less than our k value or our asymptote of -1. All that's left is to graph our function. So first thing we're always going to graph is our asymptote. So y equals -1. And now we're going to plot our 2 points. We have 2, -1.5. That's going to be right about there. And next we have the point 3 comma negative e over 2 minus 1. So to figure out that negative e over 2 minus 1, you have two options. You can put it into your calculator, or you can solve it out. Remember, e equals approximately 2.72. So if you plug in 2.72 for e, we get 3 comma negative 2.72 divided by 2 minus 1. You solve that out, you get 3 comma negative 2.4. So we're going to plot that point as well, negative 3, negative 2.4, right about there. And we know this is an exponential growth function since our base is e, or our b is e, and e is about 2.72, which is greater than 1. So we know the shape of the function will start near the asymptote, then grow away from the asymptote, just like every other growth function. So our function should look something like that. All right, and for number 2, I want you guys to try that out yourself. Pause the video. We've done problems like that in 13.2, and we went over a problem where using a base of e. So pause the video, try it yourself, and I'll post the answers in a couple seconds. So this is what you should have gotten for number 2. Let me make that a little clear. This is negative 5.7. So your transformation rule should have been x minus 2 and negative y minus 3. Your a is negative 1. Your b is e. Your h is negative 2. Your k is negative 3. Your asymptote is y equals k, so y equals negative 3. Your first reference point comes from the point 0, 1. That transforms into negative 2, negative 4. Your second reference point is 1e, and that transformed into negative 1 comma negative 5.7. Your domain is going to be all real numbers, so in interval form is negative infinity to positive infinity, and your range is y is less than negative 3. So in interval notation, or whatever notation that is, I'm blanking out on it, it's going to be y is less than negative 3. All right. So anyway, guys, that's the video. It's the end of 13.4, end of module 13, and hopefully this helped.